So the third and final issue to think through is we need to make sure that we pay the piper, that we keep these invariants maintained. We know that if they're satisfied, then we have this great way of finding the best edge in each iteration. We just do an extract min. But how do we make sure that these invariants stay maintained throughout the algorithm? So to get a feel for the issues that arise in maintaining the invariant, specifically invariant number 2, and also just to make sure we're all on the same page with respect to this definition of the key value of the vertices in the heap, let's go through an example. So in this example, I've drawn in the picture a graph that has 6 vertices. In effect, we've already run 3 iterations of Prim's algorithm. So 4 of the 6 vertices are already in capital X. The remaining 2 vertices, V and W, are not yet in X. They're in V minus X. So for 5 of the edges, I've given them costs labeled in blue. For the other edges, it's not relevant for this question what their edge costs are, so you don't have to worry about it. So the question is the following. So given our semantics of how we define keys for vertices that are not in X, so in this case the vertices V and W, what are their current key values supposed to be? So those are the first 2 numbers I want you to tell me. What's the current key value of V and W? And then secondly, after we run one more iteration of Prim's algorithm, then what is the new key value of the vertex W supposed to be? So the correct answer is the fourth one. Let's see why. So first, let's remember the semantics of keys. What's the key supposed to be? It's supposed to be amongst all the edges that on the one hand are incident to the vertex, and on the other hand are crossing the cut. It's the cheapest cost of any of those edges. So for the node V, there's 4 incident edges with cost 1, 2, 4, and 5. The 1 is not crossing the cut. The 2, 4, and 5 are crossing the cut. The cheapest of those is 2. So that's why V's current key value is 2. For the node W, it has 2 incident edges, a 1 and a 10. The 1 is not crossing the cut. The 10 is. It's the only candidate crossing the cut, so its key value is 10. So the third part of the question says, what about when we execute one more iteration of Prim's algorithm? So what is Prim's algorithm going to do? Well, it's going to move the edge with the smallest key from the right-hand side to the left-hand side. V has a key value of 2, W has a key value of 10, so V is going to be the one that gets moved from the right-hand side to the left-hand side. So once that happens, we now have a new set, capital X, with a 5th vertex. V is now a member. So the new value of X is everything except for the vertex W. Now, the key point is that as we've changed the set capital X, the frontier has changed, the current cut has changed. So, of course, it's a different set of edges that are crossing this new cut. Some have disappeared, and some are newly crossing it. The ones that have disappeared are the 2 and the 4 and the 5. Anything between the vertex that got moved, that was already spanning going to the left-hand side, has now been sucked inside of capital X. On the other hand, the edge VW, which was previously buried internal to V minus X, with one of its endpoints being pulled to the left-hand side, it is now crossing the cut. So why do we care? Well, the point is W's key value has now changed. It used to have only 1 incident edge crossing the cut, the edge of cost 10. Now with a new cut, it has 2 incident edges, both the 1 and the 10 are crossing the cut. The cheapest of those 2 edges is, of course, the edge of cost 1, and that now determines its key value. It's dropped from 10 to 1. So the takeaway from this quiz is that, well, on the one hand, having our heap set up to maintain these 2 invariants is great because a simple extract min allows us to implement the previous brute force search in Prim's algorithm. On the other hand, the extraction screws things up. So it messes up the semantics of our key values. We may need to recompute keys for the vertices. So in this next slide, I'm going to show you the piece of pseudocode you'd use to recompute keys in the light of an evolving frontier. Fortunately, restoring invariant number 2 after an extract min is not so painful. The reason being is that the damages done by an extract min are local. More specifically, let's think about what are the edges that might be crossing the cut now that were not previously crossing the cut. Well, the only vertex whose membership in these sets has changed is V, so they have to be edges that are incident to V. If the other endpoint was already in X, then we don't care. This edge has just been sucked into X. We never have to worry about it. But if the other endpoint, so of this edge incident to V, if the other endpoint W is not in X, then with V being pulled over to the left-hand side, now this edge spans the frontier when previously it did not. So the edges we care about are incident to V with the other endpoint outside of X. And so our plan is just the obvious one, which is for each dangerous vertex, each vertex incident to V where the other endpoint W is not an X, we just follow to the other endpoint W and we just recompute its key. And we just do that for all of the relevant W's. So the recomputation necessary is not difficult. There's basically two cases. So this other endpoint W, now it has one extra candidate edge crossing the cut, namely the one that's also incident on V, the vertex that just moved. So either this new edge VW is the cheapest local candidate for W, or it's not. And we just take the smaller of those two options. So that completes the high-level description of how you maintain invariants 1 and 2 throughout this heap-based implementation of Prim's algorithm. So each iteration you do an extract min. Following the extract min, you run this pseudocode to restore invariant number 2, and you're good to go for the next iteration. So for those of you who want not just a conceptual understanding of this implementation, but really want to get down to the nitty-gritty, want to dot all the I's and cross all the T's, a subtle point you might want to think through is how it is you implement this deletion from a heap. The issue is deletion from a heap is generally from a given position. And so here I'm only talking about deleting a vertex from a heap. That doesn't quite type check. Really what you want to say is delete the vertex at position I from a heap. So really pulling this off, the natural way to do it is have some additional bookkeeping to remember which vertex is at which position in the heap. So again, for the detail-oriented amongst you, that's something to think through, but this is the complete conceptual description of the algorithm. Let's now move on to the final running time analysis. So the first claim is that the non-trivial work of this algorithm all takes place via heap operations. That is, it suffices to just count the number of heap operations, each of which we know is done in logarithmic time. Okay, so let's count up all of the heap operations. One thing we already talked about, but I'll mention it here again for completeness, is we do a bunch of inserts just to initialize the heap in a pre-processing step. So after we initialize, we move on to the main while loop. Remember, there's exactly n-1 iterations of that while loop. And in each one, we extract min exactly once. So these were the easy steps. What you should be concerned about are the heap operations, the deletions and reinsertions that are triggered by needing to decrease the key of vertices that are not in X. Indeed, in a single iteration of Prim's algorithm, in a single move of a vertex inside of capital X, can necessitate a large number of heap operations. So it's important to count these operations in the right way, namely in an edge-centric manner. And the claim is that a single edge of the graph is only going to trigger a single decrease key pair of operations, a single insertion-deletion combo. We can even pinpoint the moment in time at which we're going to have this deletion and reinsertion. It's going to be when the first of the endpoints, so either V or W, the first iteration at which one of those gets sucked into the left-hand side capital X, that's going to trigger the insert-delete potentially for the other endpoint. When the second endpoint gets sucked into the left-hand side, you don't care because the other endpoint has already been taken out of the heap. There's no need to maintain its key. So that means that the number of heap operations is at most twice the number of vertices, plus at most twice the number of edges. We're again going to use this fact that the input graph is connected, and therefore the number of edges is asymptotically at least the number of vertices. So we can say that the number of heap operations is at most a constant factor times the number of edges m. As we've discussed, every heap operation runs in time logarithmic in the number of objects in the heap, so that's going to be log n in this case. So we get an overall running time of O of m times log n. So this is now a quite impressive running time for the really quite non-trivial minimum cost spanning tree problem. Of course, we'd love to do even better. If we could shave off the log n factor and be linear in the input, that would be even more awesome. But we got to feel pretty good about this running time, right? This is only a log n factor slower than what it takes to read the input. This is the same kind of running time we're getting for sorting. So this actually puts the minimum spanning tree problem into the class of 4 free primitives. If you have a graph and it fits in the main memory of your computer, this algorithm is so fast, maybe you don't even know why you care about the minimum spanning tree of a graph. Why not do it? It's basically costless. That's how fast this algorithm is.